That's EE544 with Professor Zahid on Thursday, January 30th, 2014.
Thank you very much. Good afternoon and welcome to E544 again. Let's try to finish our discussion of the overview of different architectures. Last time we looked at the transmitter architectures. We saw that we could have a what? We could have a super heterodyne transmitter where we go from the baseband to the IF to the RF, or we could have a what? Direct convergent transmitter which goes from the baseband directly or immediately to the what? To the RF. Today we are going to be looking at the receiver architecture, and again, as I told you, receivers are much more challenging to design rather than what? Transmitter, because of the presence of a what? A very weak signal, because of the presence of noise, because of the presence of what? Interferences, both intentional and unintentional, all types of what? Problems. All appear with what? All appear at the receiver side. Notice, by the way, when you transmit your signal, is it at a constant power? When you transmit your signal, is it at a constant power? Don't worry about the CDMA stuff. In general, is it at a constant power? Whereas the received power is what? Fluctuating, because it depends on the fading and the environment, the multipath, and so on and so forth. Clear? Which one is easier to deal with? Constant voltage or variable? Variable voltage is, of course, more difficult. We will look at the three types or multiple types of architectures, including the super heterodyne receiver, the direct. They call it also the zero IF. Either zero IF or sometimes they call it what? The homodyne. Homodyne receiver or the zero IF conversion receiver. Zero IF means what? You go directly from the RF to the baseband. A low IF single conversion receiver. Low IF means what? You still use IF, but the IF is very close to the what? To the baseband, very close to the baseband. Now you might say, well, how is that different than this one? We'll get to all of these issues in a minute. Clear? Okay, we will also look at some wideband IF with double convergence. We will also I'll give you an overview of software-defined radios and so on and so forth. Clear? Okay. Let's start first of all with the super heterodyne receiver, the heterodyne receiver. Remember, by the way, it's in the same module. So this is the what? Transmitter. This is the what? Receiver. That's why we call it a what? Transceiver. Okay. But we are interested right now in this section. Clear? In this section. Now, first of all, let me ask you a question. Is it possible that the signal comes in here and leak in here? It is possible. Which means what? We need to make sure that this duplexer is what? Is isolated enough between the receiver and the what? Transmitter. Some cases, as I told you, for example, in the cellular, the transmission frequencies and the receiving frequencies are different what? Different band, separated enough from each other so that they don't cause interfere. And by the way, if this one goes to here, what does it mean? You are interfering with who? With yourself. Well, you are interfering with yourself. Clear? So let's not worry about that right now. The signal is received over the what? Over the radio. What is this one is doing? What is this filter is doing? This filter here. By the way, what type of filter is this? That's a bandpass filter. A bandpass filter. What is it doing? It is rejecting all out-of-band channels. All out-of-band. Clear? No response. Clear? All out-of-band channels. It will pass all what? All in-band channels. All in-band channels. Okay. Now, it comes in here. Again, I need to have a what? A low-noise amplifier, variable gain low-noise amplifier to make sure what? To make sure that we can boost a little bit of what? Boost a little bit of the strength of the received signal. The received signal is weak. But I don't want this one to introduce a lot of noise internally, because as I will show you shortly, It is the noise figure of this device that will determine what is the overall noise performance of our receiver. Clear? The first component is the one that will that will determine the overall. Clear? Okay. So we need to make sure that this is what introduces very little noise in it. What is this filter here? Can you zoom in please a little bit? Hey, thank you very much. What is this filter? Which we'll talk about it in just a second. Question. Is it a bandpass filter? That is called what? The image rejection filter. This one we call it the image rejection filter. And we will talk about this in just a second in detail, how they design image rejection filter. What is an image means? What is an image mean? One more time. Is it possible that do you understand what image frequency means? Image frequency is a frequency that is separated from the what? From the local oscillator by the same value as the what? As the desired channel, as the RF channel. Yes? Is it possible that the image frequency is out of band? Out of band of interest. Is it possible? When? When the IF frequency is what? Relatively what? High. The image might be outside. And if it is outside already, then it means what? It means that this one has already what? Attenuated severely. Clear? But in general, it might not be outside. So which means what? It means that we need to what? We need to filter it before what? Mixing. Why? Because if it is after mixing, it is what? Too late. Do you understand what too late means? Means it will be, as I will show in just a second, it will be overlapped with the what? With the IF. It's too late then. It becomes what? I cannot filter it outside. Okay, we'll get to that in just a second. This is a down converter. Clear? This is not the demodulator. This is not the demodulator. Do you see IQ here? You don't see IQ. This is just a down converter, down converting from what? RF to what? IF. Does it down convert the entire band or only one channel? It will down convert the entire band. Are you following? I will show you that in just a second. It will down convert the entire band that passed through this from where? And instead of being centered around what? RF, it will be centered around where? IF. Clear? That's this local oscillator. We call it what? UHF. UHF stands for what? Ultra high frequencies. Ultra high frequencies means what we are talking about what? For example, 300 megahertz to what? 3 gigahertz and so on, so or more than that. Clear? Okay. Now keep in mind always that when you are dealing with what? When you are mixing, you are going, ideally, you are going to get the sum and you are going to do what? You are going to get the what? The difference. Which one am I interested in? Difference. Question. Is this a fixed local oscillator or is it a variable? That's a variable. Are you following on now? Is the desired channel, could it be different desired channel? It could be different desired channel. The difference between the desired channel and the what? Local oscillator is what is referred to as what? IF, which is fixed. Clear? Okay, as I will show you in just a second. What is this one doing? This one. Anybody saw? Surface acoustic waves. Those are bulky filters. Bulky filters, most of the time, they are what? They are of the chip. Clear? As I will show you in just a second. What is, by the way, what is IFA? IF amplifier. Are you following me on that? Again, remember what I told you last time? You try to distribute the gain across the what? The receiving chain. Not only in one block. So we have, for example, the LNA, we have the IFA. What is this, by the way? VGA. VGA stands for what? Variable gain amplifier at the output of the filter. Clear? Across, by the way. And then we also have what? We have amplification within the what? Within the baseband, within the digital domain. Clear? Okay, good. Now, what is this? What are we selecting? What this is the channel selecting. In here, I'm going to select the desired channel among what? Among all other channels within the desired what? Within the desired band. So this is the channel selection. This is the what? Band selection. Question. Can we select the channel here? To just select the channel here, we need a filter. Remember the Q of the filter? What is the Q of the filter? F sub C divided by what? The bandwidth. The channels are what? Narrow band channels. F sub C is very high, which means what? The ratio of F sub C divided by the bandwidth will be what? Extremely high, which means we need what? Extremely sharp, high order filters to select the channel right away. Clear? Okay, that's why we call super hydrodynamic. Good. Now, once you reach this, what am I going to do? What is the purpose of this guy? This is the demodulator. Again, the IQ. By the way, when we get to the modulation, for time being accepted. When we get to the modulation, I need to explain to you why are we splitting this into the I and the Q. Why we use IQ. For time being accepted. We will get to it shortly in detail, just for time being. What am I using here? Is that another local oscillator? Yeah. By the way, what am I doing the IQ? I'm doing the IQ in the what? At high frequency or at low frequency? Low frequency. The performance of IQ in terms of what? Symmetry. Are you following on symmetry or the drifting offset is much better at what? At baseband, at local, at low frequencies rather than what? High frequencies. Clear? We have a VHF. VHF is the what? Is the very high frequency local oscillator. Yes? Well, what? Well, by the way, what is this? This one? 090 means what? Phase shift? Let me show you the phase shift. This is a good point. Can you wait a second? We'll continue with it. Let me show you. How, aside. We'll detail later on, but let me just show it you. Aside. How do we design a 90-degree phase shifter? Question, is this phase shifter at a single frequency? Say that again? No, why? This is just a local oscillator. Why is it local? I have just one frequency. This one here, this is just a single frequency. Did you get this or not? What is this? We hear noises. What is that? Interference. It's 9-phase shifter. Okay, this is a simple design, but just to get an idea about it. This is I want you to tell me something. I want you to see this circuit. This is the input. Yes? This is the input. I want you to tell me this circuit. What is it? That's a low-pass filter. You agree? What is this? High-pass filter. Yes or no? Let's take one of them so that you understand what I'm talking. Did you get it or not? This is a what? This is... What is this? Let's take one of them just to see what we are talking about. This RC. I will get back to our discussion in just a second. I want to show you one thing here. Can you tell me what is the frequency response? What is the frequency response of this circuit? It's what? H of what? Omega. Can I keep it in terms of omega? Okay. H of omega is what? 1 over J omega C divided by what? R plus what? 1 over J omega C. You agree? Yes. Which is what? 1 over 1 plus J omega R C. You agree with me on that? Yes or no? Okay, question. Can I sketch it or do I need to break it into magnitude and phase? I need to break it into magnitude and phase. Why? Because it's complex. What is the magnitude? Absolute value of H of omega is what? 1 over 1 plus omega square R square C square. The whole thing what? Square root. And how do I sketch this? This is how I sketch it. Yes? At this point, what is this? What am I sketching? This is at omega. What is this value here? This value is what? Omega is what? 1 over what? RC. And what do I call this one? That's the 3 dB point. So if this one, this is what? 1 over square root of 2. You agree? Okay. Yes or no? But I'm more interested in the phase. I am more interested in the phase. Okay. What is the phase? Because this is a phase shifter. What is the phase of this guy? The phase of this guy is what? Give it to me. Give it to me. It's tan minus tan inverse of what? Omega RC. Which is what? How do I sketch it? Help me, help me. Is it linear, by the way? Tan inverse. Yes, this is what? Omega. This is what? Phase of omega. Did you follow me or not? Okay. What is the 3 dB? Sorry, when omega equal to what? 1 over RC. What is the phase? What is the phase? Minus 45 degree. Yes? Cannot hear you. Question. Can I choose this omega? Remember, what is the unknown? When you use this circuit, what is the unknown? The R and the what? C. The omega, can I use this one as omega naught? Which is the desired, which is this frequency. This one. Yes or no? I choose it to be what? 1 over RC. In other words, I will choose RC such that the inverse is what? Is that omega? Yes or no? Which means the phase difference, the phase shift at that omega will be what? Minus 45 degree. Yes or no? Guess how much will it be on the high pass filter at that omega? This is a high pass filter. Guess how much the phase difference will be? Plus 45 degree. Yes or no? Which means, what is, if I look at between this value, this port and this port, what will be the phase difference between them? 90 degree. Do I need to show it to you, or let me assign this for homework? But did you get the idea? I showed you the low pass filter. Yes? If you do the high pass filter, you will see that the phase at omega naught, by the way, omega naught will still be what? 1 over RC. But you will see that the phase is what? Plus 45 degree. So in here we are getting what? Plus 45 degree at what? At omega naught. And here I will get what? Minus 45 degree at omega naught. What is the difference? What is the phase difference between them? 90 degree, which is what I'm looking for. Remember, it's a sine and a what? This is a sine and a cosine. Yes or no? Cannot hear you. Hard or simple? Very simple. R and C. Are you following me or not? But keep always in mind that this is going to cause somewhat amplitude degradation. You do understand that, right? Because the magnitude is what? The magnitude is not constant. For the filter not to cause any magnitude distortion, it should be what? It should be flat in the band of interest. This one is not going to be flat. Clear? Okay. But we'll talk about this circuit later on. I just thought about it and wanted to show it to you. So let me write the comment here. From the high pass filter, we will get the phase of 45 degree at what? At omega equal to what? Omega naught, which means what? Let me put this one. Port A, port what? B, which means the phase difference between points A and B is 90, thank you, it's 90 degree. Clear? Clear? Now, later on, we will also design phase shifters over a range of frequencies rather than only what? Rather than only single frequency. Have you taken courses in communications? Pure communications, anybody? Nobody? Have you heard about Hilbert transform? Hilbert transform is going to be used to generate what? To generate a phase shift of what? 90 degree for what? For all frequencies. Clear? Clear? Can you show me how does it look like? Not the Hilbert transform. Can you show me a characteristic of a phase which is what? 90 degree for all frequencies. It looks like what? Agree or not? No response. Notice, by the way, why is this like this? Keep in mind, the phase is a what? Is an odd function of the frequency. Are you following me or not? Yes or no? What is this, by the way? This is omega. And what am I saying? It is what? It's providing me with a 90 degree phase shift over what? Over all omega. But that's easier said than done. By the way, is this ideal? This is, I mean, it's this, to come up with this characteristic, we need what? Ideal design, which we cannot do that. Clear? But we'll talk about that later on when we get to the modulation techniques. Clear? Clear? This one, it's recall Hilbert transform. By the way, this might not mean anything to you right now if you have not taken any courses in communication. So even if you don't get this, don't worry about it right now. We'll get to it shortly. Okay, so, yes.
If the R and C values are same for the low pass filter and high pass filter.
If the what?
If the R and C values of the low pass and the high pass filter are same.
Yeah, so the omega naught will be the same.
Yeah.
But it's different phases.
So it doesn't matter whatever local oscillator frequency, it will always be 90-degree phase shifted if we calculate the transfer function.
I didn't get your question.
If the resistance
You are going to choose the RC such that 1 over RC is equal to what? Omega naught. So if you change omega naught, the values of R and C will what? Will change. I'm not sure I got your question.
my question is that no matter what R and C value we choose, provided that the R and C values are same for both the low pass and the high pass filter, for all frequencies they will be 90.
What do you mean for all frequencies?
For any frequency, for omega naught.
No, my dear, it has to be minus 45 degree. I'm not sure that I understood your... In other words, are you telling me I take a frequency here? The frequency will not be minus 45. I need the minus 45. I still did not get your question. Can you ask after the class? I am not getting your question. The reason that I chose omega naught to be 1 over RC to get the phase of what? Minus 45. If you choose different values of RC, you are going to get for the same frequency. For the same frequency, you are going to get what? Not 45 degree. You will still get what? Minus and the plus. Yes? But it's the sum is not 90 degree. Yes or no? Not sure. Did you get it or not? No. Not sure. Let me go back one more time. What is the phase here? When is this 45 degree? When omega is equal to what? 1 over RC. If omega is not equal to 1 over RC, let's assume omega is not equal to 1 over RC, some different omega. Yes? Will this one be 45? Yes or no? Give me a value. Give me just a value, just a regular. Let's say it's minus 30. Yes? Then what? And then from the high pass filter, what is the difference? 60. It will not be 90. I want 90 degree because it's what? One of them is sine, the other one is a what? Cosine. Clear? Clear? Okay, good. Yes. I cannot hear you, my dear.
We use I equal to 1, we use C equal to 1, and we get the omega O equal to 1. But we can choose R equal to 2, C equal to half, then we can still get omega.
That's true. So the values of R and C will determine the design.
Yes, the question is that should we choose the RC value with the same omega O, or we should choose R1 equal to R2 and C1 equal to C2? From the low pass filter to the high pass filter. The RC should be equal, or the times should be equal.
I'm still not getting the question. I give up. What I'm trying to say is that the phase needs to be what? 45 degree at the desired frequency.
Yes.
So this is given. This is not unknown. Is this your question?
Yes.
This omega naught is given.
Yes.
What you are saying is, let's just for the sake of argument, let's assume that omega naught is what? Is 1.
Okay.
Just an example. This RC, you could choose both of them equal to what? 1. Or you could choose what? R equal to what? 2 and C equal to what? 1/2. Is that your question?
There are two branches. There is a high branch.
Let's do the high pass. I made a mistake bringing this one into it. It's the same analysis. Let's look at the high pass. What is the high pass? This is the high pass. Yes? C, R. So what is the H? Equal to what? R over what? R plus what? 1 over what? J omega C, which is equal to what? J omega RC over what? 1 plus J omega RC. Do you agree? Okay. Oh, sir, hey. I cannot hear Mr. talking while you are talking. Continue.
There are two branches. There is a high pass branch, there is a low pass branch. And there are 2R and 2C because there have individual in each branch. So I mean, should they are the same? Should the R...
Let's do it. We started doing it. Let's continue doing it. Can we continue doing it?
Yeah.
Okay. What is the magnitude of H of omega first? Omega RC over what? Square root of what? Yes? Yeah, the absolute value of this is just omega RC. And what does this one look? Yes? What is this? Omega at omega equal to what? 1 over RC, you get to the what? The 3 dB. Yes? And what is the phase? Tan inverse of what? Yes? At omega equal to 1 over RC. What is this? 90 minus 45? 45. So what is the problem, sir? I don't understand what the problem is. It's at omega, Okay, if we don't get it, you need to see me after the class. We cannot do that. At omega naught equal to what? 1 over RC. The phase of H of omega is what? 90 minus what? Which is what? 45 degree. Which means what? From here I'm going to get what? 45 degree, and from here I'm getting what? Where is it? Oh, I'm getting minus 45 degree. Clear? Okay. I'd say we spent too much time on this circuit. No, sir. You put your hand down. On this? Sir, I need to move on. So after the class, what is your question quickly?
My question is that, is it possible for the two resistance for the low pass and high pass to be different?
My dear, what difference why is this bothering you? The important thing is that each one is providing for what? 45 degree. So if you choose, by the way, why do you think, if wouldn't it be easier if you use the same?
Yeah.
So why? What I'm trying, oh, his question is why could they be different?
Talking about the matching, because you use different values of R, and the matching will be difficult to achieve this question. Yes, you can. If you use the same R in the low pass branch and the high pass branch, the problem will be very easier. But if you use different value, you can still get it. The phase shift in the omega 0, but the matching problem will be difficult to achieve.
What problem?
Matching.
My dear, we are not looking at the overall picture here.
Yeah.
We are going to talk about the matching in detail. Give me a break. Here, I just showed you a simple circuit to provide for what? To provide for 90 degree. By the way, when we get to the matching, we are going to see, we try our best to avoid using resistive elements. Do you follow me or not? Because resistive elements results in what? Results in loss of power. We are trying to match the power and try to eliminate or minimize the amount of power that will be what? Dissipated as heat. Clear? Clear? Okay. Be patient. We will get to this. I did not understand his question. So the question is whether we use the same R or whether you use the same R and the same C. Use the same R and the same C. Okay. Now, let's continue with this, please. Oh, my goodness. It took half an hour just to go through this. Okay. So this one here, again, is the demodulation. This low-pass filter, why is it low-pass filter? Why do we need a low-pass filter here? We need a low-pass filter because the mixer is going to generate what? Two sides. Clear? We need to what? We need to just keep one of them. Are you following me on that? Okay. We need an amplifier just to just what? The audio level. This is for the audio level. Clear? And then, of course, we need the what? The ADC. ADC stands for what? Analog to digital conversion because we are going to perform all the processing, baseband processing, including decoding, demultiplexing, the encryption, and so on and so forth. All of it, we will do it in the digital domain. Clear? Clear? Okay, anyway, that's fine. That's fine. We'll get to all of these issues shortly. I'm not going to let you go without dealing with every possible problem throughout the semester. The matching, the attenuation, all types of this, the nonlinearity, the noise. Just be patient. We'll get to it, all of it. I cannot show it to you all in one lecture. Cannot do that. Okay, so this, again, as I showed you this, all of it, the band pass filter, duplexer, reject out of band, low noise amplifier, the high Q to reject what? The image frequency, and the entire RF band. Let me show it to you so that you understand what I'm talking about. I wanted to, first of all, let me show you the mixing. This is how you translate the frequency. We already know that. This is what? You are going to get the sum, and you are going to get what? The difference. Either you select this one or you select this one. At the receiver, you select this one. At the transmitter, you select what? This one. I want you to see the diagram right now. Let's see if you can help me. What is this? What is this one? That's the band of interest. Yes? What is this one? Just this one. This one. That's the channel, the desired channel. Yes? This whole thing is here, centered around what? This whole band is centered around some frequency. Clear? Clear? When I mix it with the local oscillator, which is of what? Variable. Yes? What am I going to do? I'm going to move all of this to the IF. Yes or no? And then what am I selecting? I'm selecting only this one. Did you get it or not? I am selecting this one. By the way, this filter, now it's easier to design. Why? Because the IF frequency is what? It's relatively low. I refer relatively low. So the Q is what? The Q is the center frequency divided by what? Divided by the bandwidth. It becomes a relatively what? A relatively low. Clear? Clear? Okay, good. Now, what are these, by the way? What are these? These things, see? These are the what? These are the in-band. Still, there are some, but their effect is what? Negligible. Why? Because this filter going to take what? This is not an ideal filter, so it takes some of these also will pass through, but their effect will be what? Will be negligible. Clear? Okay, good. Now, let's get to the concept of the image. How do we get rid of the image? First of all, what is the image? What do I have here? I have the local oscillator. Yes? This is what? This is the desired channel. Yes? Yes or no? Let me ask a question. Is there a component at omega C? Is there a component, a carrier component at omega C? Or is it centered at omega C? There could be a component at omega C if there is a what? If there is a discrete component of omega C for the purpose of what? Making the synchronization at the receiver easier. Yes or no? Yes. See, there is some, for example, have you heard about double sideband suppressed carrier? What does that mean? You are not going to send a what? A carrier component. So the spectrum will be centered around what? Omega C. But when you talk about what? AM, AM means what? It's double sideband, but there is also a what? There is a carrier component in it, omega C. This is omega naught. Clear? The local oscillator. This is what we have. This is what? This is the mirror signal or the mirror image of what? Of the desired signal. Yes? The center frequency is what? Is here. What is the difference between the local and the what? The desired. By the way, what did we call this? High injection. High injection means what? The local oscillator is greater than this. Yes? What is the difference between this one and this one? IF. What is the difference between this one and this one? IF. When you what? When you mix it, both of them are going to what? IF. Can you remove it? You cannot remove it because it's already now what? It's already right now copying the same band. What we need to do is what? Get rid of this before what? Before mixing with the what? With the local oscillator. Did you get this or not? And I will show you how they do it in just a second. But clear? Clear? Okay, good. One more time. What is the center to center between the image and between the desired and the image? to IF. If you make IF large, what does that mean? It means the desired frequency and its image are what? Far away from each other, which means what? It makes it easier to what? Filter out the what? The desired, and getting rid of the what? Of the image. We don't need, let me show it to you so that you can see it. I want you to see this. What is this? That's the image. That's the desired. What is the difference between them? 2IF. Is it far? Relatively, is it far? Look at the filter that I used. Is this a sharp filter or not a sharp filter? Not a sharp filter, which means what? It means all of the adjacent channels, will what? I'm not talking about the image. I'm talking about what? Show it to me here. Where are the adjacent channels? This is an adjacent channel, adjacent channel. Yes or no? All of them will go through what? All of them will go through this filter rather what? Rather easily. If you make omega IF shorter, what do you need? The filter, this filter, which is the image reject filter, needs to be what? Sharper. Are you following? If it is sharper, it means what? It is more complicated. The Q is what? Is higher, but it will get rid of what? It will get rid of what? The adjacent channels, which means what? It will make it a little bit easier on the what? On the IF, on the channel select. Did you get my point on that? That's the trade that you need to make. So insert the image reject filter IR between the LNA and the mixer. Where does it go? One more time. Where does it go? Where is it here? Here, this one. It's between the LNA and the what? Mixer. Before you mix it. After you mix it, it's what? Too late. You understand that it's too late? After you mix it, it's too late. Already what? It's already okay. It's already overlap in the band. Yes or no? By the way, how come I made this one bigger than this one? Could this one be closer to the receiver? Yes or no? Another transmitter closer to the receiver, transmitting at the what? At the image of the desired channel. Clear? Okay, good. Okay, so the practical issues again involved in a single stage IF trans. What does single stage means? Single stage means what? Going from an RF to IF to what? Baseband. Could there be multiple IF stages? Multiple IF stages means what? RF, IF1, IF2, baseband. That's multiple IF or double IF. Did you get this or not? This is a single IF. The mirror frequency unwanted is located at what? At FC plus what? To FI. FI is the image. The mirror frequency has to be suppressed before it is mixed to the IF. The required filter is a high frequency with narrow bandwidth. The effective Q will be what? Must be higher roughly than what? Than 20. Clear? Roughly than 20. This can be done again with an object filter. The regular IF must also have what? Large. What is the regular IF will do? The filter. They select the channel. So it must also have a large selectivity of the order of what? Of 50. And the filter order is usually greater than what? Usually equal or greater than what? 8. Just some figures. Clear? This is pretty what? Pretty high. Yes. Which one? Yeah, the selectivity. Selectivity means what? Means 50. Means what? Means even if the what? Even if the desired signal was what? Lower than the adjacent by a certain value, you should be able to what? You should be able to select it. Selectivity means what? The decay of the decay. The fall of the what? Of the filter characteristic, which translate to what? To Q. Did we discuss this before or not? When we're talking about the filter, the properties, the last bullet was what? Was the selectivity of the filter is a measure of what? Is a measure of the Q. Clear? So when you say Q, 50, it means what? Do you notice, by the way, it's not dB or something. It's just 50 Q. Clear? 50, that's the Q. Clear? Okay. Modern application require higher RF frequencies, 0.9 or 1.8 or 2.5 is the what? Is the Wi-Fi. The 1.8 is the PCS band in the US. Clear? The 0.9 is the GSM, 0.9 GSM or the cellular, while keeping the same what? Bandwidth. Is this small? 30 kilohertz, by the way. This is the narrow band. 3 megahertz, or it could be what? Could be for some examples could be what? Could be the Wi-Fi and so on and so on. Clear? The Wi-Fi actually is more than 30 megas, 20 megas. The ratio of the RF frequency desired bandwidth makes integration of a single stage receiver very what? Very difficult. The trade I just told you about. If you use IF high, the image will be what? Greatly attenuated, whereas the adjacent channel interference are what? Not. The one I showed you, this one. This one. Clear? If you make the what? If you make the IF small, then what do you need? If you need a sharper filter in the what? In the image rejection, but a more what? A more loose filter on the other one. Clear? So you need to make some kind of a trade-off. Clear? Okay. Notice, by the way, if the image reject filter is external, the LNA must be able to drive what? A 50 ohm load. Are you following? Because you are going to go off chip. That's for what? That's for the matching stuff. That we will talk about it in detail. By the way, we will also cover transmission lines so that you understand how you deal with what? Connecting devices to another device via transmission lines. Clear? Okay. Transmission lines usually is not part of the RF classes, but we will go over it in detail. We need to understand how it works. Now, let's look at a couple of receivers that are used to cancel the image. Remember, where is this taking place? Before the mixer. Before the mixer. We have two types of receivers that are widely used. The first one is called the Hartley, which I will show it to you. The second one, I will show it to you, the Weaver. I will show you the math a little bit, but I will assign it for homework so that you understand the difference. Let's look at the Hartley first. Let's look at the Hartley. This is the what? Again, this is the band select filter. Yes, from the antenna. This is the what? Low noise amplifier. I'm going to mix it with a what? With a sine and cosine. Yes? And then what? I'm going to filter it, but I'm going to introduce what? A 90-degree in here. Are you following me or not? A 90-degree in here. By the way, either you put a 90-degree here or you put a what? It's minus 90-degree here. In other words, there must be what? A 90-degree separation between what? Between the I and the Q. For this 90-degree, by the way, you could use this simple circuit that I just showed you. Are you following me or not? Okay, good. Now, let's do the analysis. Is the diagram clear? Is the diagram clear? Let's do the analysis. Let's see if you can follow me the analysis. Can you zoom in, please, a little bit? More? Yeah, okay, good. Yeah, that's good, that's good. Okay, what do we have in the signal? What do I have the signal? The signal here is what? Can you give me what is the signal here? It's what? A. Okay, let's forget the A. In other words, let's assume the amplitude is what? 1, to make things simple. What is it? Cosine omega RF T. Yes? No response. Yes? Plus what? Cosine omega IM T. What is IM? The image. Yes or no? No response. Yes or no? Okay. Now, it will go through what? Let's calculate the I of t. This is the I of t now. Clear? Yes? What is the I of t? Is this multiplied by what? Cosine? What did you say? Why is this not clear? Okay. Okay, let's derive it in the notes. It's not very clear. Okay, so what do we have? The input is what? The input, let's call it x of t, for example, consists of what? Consists of omega RF, sorry, cosine omega RFT plus what? Cosine omega IMT. T. This is what? Cosine omega LO T, and this one is what? Sine omega LO T. This is the I channel, and this is the what? The Q channel. Let's concentrate on the, let's assume, by the way, assume high side injection. What is high side injection means? It's omega LO is greater than what? Omega RF, but less than what? Omega image. Agree? Okay, so what do I have? Look at this one here. It's what? Cosine. So at point A, we'll put the 90 degree in just a second. At point A, what do I have? We have what? Cosine omega RF T plus cosine omega IMT multiplied by what? Cosine omega LOT, which is what? Which is 1/2 cosine omega LO minus omega RF T. Yes? Okay. Notice, by the way, the sum I'm going to eliminate it anyway. Did you get my point? In other words, I'm not going to write it because after each one of them, there is a what? There is a filter. Clear? I'm only interested in the desired one. Okay, plus what? Omega IM minus omega LO T. Agree? What happened one more time? What happened to the sum? The sum will be filtered out. Clear? Hey, how about this one? How about this one? How about this one? What will it be? So point B. What do I have? I have cosine sine. Yes? What is cosine sine? Sine, and the other one is also what? Sine. Both of them are sines. So what do I have at point B? We have the following: 1/2 sine omega LO minus omega RF T. What is it? Plus or minus? Sorry. The sum is what? Filtered out. Yes. Plus what? Sine omega IM minus what? Did I make a mistake? Huh? Is this minus or this is plus? Can you check the trigonometry? What is it? Sine? Is it minus or is it a plus? See, what I'm trying to tell you, check this one if it is minus or plus. What I'm trying to tell you is that, see this term and this term? If you are going, see this one, which one is omega LO minus omega? If this is minus, let's assume this is minus. And if you are, I'm not sure if it's minus or plus, you need to check it. And if you introduce a 90 degree, either in here or what? In here, what will happen? What will happen is that one of them will what? Switch phases, yes? And the other one will be what? Will be additive. Do you follow me or not? Yes. Which means what? One of them will cancel and the other one will what? Will be added up. Clear? I think this one is negative. Can you check it? Trigonometry? This one is plus? And if you put minus 90 degree, if you put a minus 90 degree like this one, minus 90 degree. Do you see this minus 90 degree? Yes? What will happen? What will happen is that one of them will become what? And when you what? When you when you add the output, you will see that the what? That the desired will what? Add up, and the image will what? Subtract. I'm not sure if this is minus or plus. You can do it trigonometry. Yes.
There is an addition in the second term of the sign.
Where?
At the bottom.
This one?
No, at the bottom of the page.
This one?
The second term.
This one?
No, at the lower one, yeah. This one, yeah. Second term, there's an addition between the two frequencies. The value IM and the value LO. The two frequencies are added together.
Add? This one will be filtered out.
Ah, sorry.
The sum will be filtered out. You just keep the difference. Clear? See, I think this one is what? Is omega LO minus omega IM. But because omega LO is less than omega IM, it will become minus. Because remember, the sign is a what? Is an odd function. Clear? Somehow this is a minus sign. You follow me or not? Check. It's just the trigonometry. Can you check the trigonometry, please? I understand that, but this one is what? Is sine omega LO minus omega IM. So when you reverse it, it becomes what? Negative, because I wrote it omega IM minus omega LO. In here, it doesn't matter because the cosine is a what? Is an even function of omega. Did you get it? Yes or no? Okay. When you put a 90-degree phase shift, what will happen? Yes. Huh?
From the picture, if you put minus 90 degree, it will happen in the function 1.
This one?
Yes, you mean this one is cosine. So,
insert the 90-degree phase shift in either the I plus or minus I or the what? Q channels, and somehow you check it trigonometry, somehow the image will what? Will cancel out. Are you following me or not? Figure it out yourself, whether it's plus or minus. Is it that hard?
no.
It's not that hard. It's trigonometry stuff. Clear?
Yes.
Okay. Let me ask you a question. What is the difference between this one and this one? This one and this one. Are they the same circuit? No, they are not the same circuit. Why? This one is establishing a what? A 90 degree over what? One frequency. Whereas this one is establishing 90 degree over what? Over the entire band. Did you understand that or not? That is the one that is challenging. This one is not. Clear? Now I want you to see the next one, which is called what? Weaver. Tell me the Weaver. Weaver image is a little bit more widely used. The Weaver. Let's see the Weaver before we do the analysis. Again, this is the same thing. The band select and the LNA. Yes, it goes. I go into multiple what? IQs. Multiple IQ. 2 IQ. One at omega 1 and the other one is at what? Omega 2. I will do the analysis in just a second. Okay, but in doing so, what did I eliminate? I eliminated the need of using a what? Did you get this or not? That I don't need this one. Remember, this one is hard to design because it's going to provide 90 degree over what? Band. There's in here nothing. I don't use that, but I'm going to use what? A couple of what? Couple of mixers, IQs. Clear? Let's do it. By the way, in here, I will let you read this at home. This is in the frequency domain. In the frequency domain. Let's do it in the what? In the time domain. Can we do it? Let's see.
The time is 20 o'clock.
Now, first of all, assume both local oscillators are high side injection. Let's see if you can help me here. This is point what? Point A, and this is point what? Point B. A, B, and this one is point what? C, and this one is point what? D. Clear? Okay. High side injection for both. Give it to me. The input is what? Agree? I am going to multiply by what? Cosine omega 1t. So what do I get? At point A, and remember, by the way, this filter will get rid of who? The sum. So I'm looking only at point A. What do I have? At point A, what do I have? 1/2 cosine. Help me. Omega 1 minus what? RF T. Why? Because this one is what? Is the high side. Plus cosine. Cosine, help me. Omega. IM minus what? Omega 1 T. Close the bracket. Clear? Clear? Okay, at point B. Again, the sum has what? Get rid of this one here. At B, what do I have? 1/2. Remember, I have what? I have cosine sine. Cosine sine means what? I get both of them what? Sines. Yes? So what is it? 1/2 sine omega 1 minus omega RF T minus. This minus is the same reason that we just did. So it's what? Minus sine omega. Help me. IM minus omega 1 T. Close the bracket. Yes? Okay. Now, again, we are saying assume what? Assume low, high side injection, which means what? Omega 2 is greater than what? Omega 1 minus what? RF. Do you agree? This is now the desired. Don't worry about them. This is the desired. Yes? Yes? So omega 2 is greater than omega 1 minus omega 1. So at point what? At point, help me. At point C, what this is, I multiply with cosine. Yes? So what do I get? 1/2 cosine what? Omega 1 minus omega RF minus omega 2. Did I mess up? But the cosine is even. The cosine is even, doesn't matter. Yes or no? Okay, plus 1/2 cosine omega IM minus omega 1 minus omega 2 T. Clear? Okay. And on the other side, at point what? D. What am I multiplying? This with a sine. Yes? Sine, sine is what? Cosine, cosine. Yes? So what do I have? Help me. 1/2. My dear, let's not get bogged down with 1/4. 1/4, this one 1/4? This one? Oh, 1/4. Don't get bogged down with the important thing is that we need to see, are we going to get rid of the what? Image. Of the image. Don't get bogged down with the okay, 1/4. Because we are multiplying cosine, cosine. 1/4, you are right. Okay, which is fine, Okay, what am I multiplying? With the sine. Yes? Sine, sine is what? Cosine. So what do I have? Cosine. Omega 1. Help me. Minus omega RF minus omega 2 t, yes, minus sine, minus cosine, help me, is it minus? Mine, omega I m minus omega 1 minus omega 1 minus t. Did you get it? Yes? Check this minus and plus. Yes or no? Okay. Now, if you add them together, what will happen? Help me. What will happen? This, why is this 2 1/4? And this one is the whole thing. Yes? This will cancel with this. You agree? This will add up with this. Yes? What is the IF? What is the IF? It will be what? In other words, listen to me. Is this minus or plus? It's minus. If you make omega 1, 1 second. If you make omega 1 plus omega 2 equal to what? RF. You are going to go from center to what? 0. Did you get this or not?
Yes.
Which is what? You are going to get rid of what? You are not going to get a what? What's known as a secondary image. What does a secondary image means? Let me ask a question. Is it possible that an image will be created here?
Yeah.
Yes or no?
Yes.
There was an image here. Is it possible that another image is created here through the choice of what? Omega 2. Yes?
Yes.
But if you choose omega 2 such that this term will be equal to what? 0, it means you went from what? RF directly to who? Baseband, which means you did not create any what? In your image. You did not create a new image. Agree? Yes or no? So what is it now? See, if you add, we get, what do we get? 1/2 cosine omega 1 minus what? Minus what? T. This one will what? Will cancel. Where is the information centered? The information here is centered around what? Remember, this it was centered around what? Omega RF, but now it has been what? Shifted toward what? Omega RF minus omega 2. How can I write this in a different way? In other words, omega RF minus omega 2 minus omega 1, like this? Like this? Okay. Or I can write it like this. I think it's better to write it like this. Omega 1 minus omega 2 minus what? Omega RF. Clear? Which means what is the IF now? What is the IF? Is the omega 1 minus what? Omega 2. I translate it from the RF all the way to what? By what? Omega 1 minus omega 2. Clear? Clear? I will assign this for homework. I don't want to get into trigonometry stuff. Jeez. Okay, with the proper choice of omega 2, we can what? We can also convert to what? Baseband directly, which means what? Eliminate the possibility of creating secondary, they call it secondary image. What is the primary? The primary was at the beginning. Are you following that? This one, if you are not going to go to all the way to 0, there's a possibility that you will end up with what? With a small secondary image. Clear? This will be assigned what? Homework. I don't want to get into the trigonometry stuff. Jeez. It's straightforward, by the way. Don't assume this is hard. It is straightforward. But you need to keep track of what? The trigonometry. You follow me or not? You need to keep track of the trigonometry. Clear? Okay, good. Let's continue. By the way, this shows you also what happens to the spectrum. Let's look at the frequency domain so that you get the idea. What is this? This is the desired channel. In this diagram, it's what? It's low side. Low side injection. This is the what? Desired channel. This is the image. When you multiply with cosine, what are you going to get? You are going shifted to what? To omega, by omega 1. Yes? This one multiplying by sine. Tell me, why did it become like this? Because when you multiply by sine, you are, what is, by the way, what is the Fourier transform of sine? First of all, cosine. Cosine. Cosine omega RF T. What is the Fourier transform? 1/2. Yes? What about the sine? Agree?
Yes.
So there is a J in there. That's the J. You see this J?
Yes.
Yes or no? And because it's minus, so it becomes like this. Agree?
Yes.
And then what? Again, multiply them again. This is what you get. The image will what? Will cancel out. The image will cancel out, and you end up with what? You end up with just the basement. Clear? Clear? Okay, now, the measure. I want you to remember this very important ratio. It's called what? IRR. IRR stands for what? It's written here. Image rejection ratio. Image rejection ratio. Listen to what how we define the image rejection ratio. Let me define it first. Power. You do understand when I say power, everything is what? Average power. Clear? Okay, power in what? Image. In what? Divided by what? Power. Not in. Power of desired. In what? IF band. Divided by what? Power of image in RF divided by what? Power of desired in RF band. This is like this. It's measured in what? In dB. Clear? Clear? Okay. Tell me, what is this? What is this? What are we talking about here? Epsilon and theta. What are they? You see those IQ? Are they ideal? Is it possible that they are not balanced? Yes or no? If they are not balanced, answer me the following question. Will these cancel out? When we do a trigonometry, will they cancel out? Notice, by the way, in this analysis, what did I assume the amplitude is? 1. Yes? Is it both of them exactly 1? In other words, could one of them have a what? Could one of them have an 1 plus epsilon? In other words, one of them is this. And the other one is what? Did you get it or not? We have what is known as what? Amplitude what? Error. Are you following that? Because the IQ are not what? Are not balanced, are not matched. Clear? Could we have a phase error? That's this phase error. And you can see if we have epsilon 5%, and if we do have what? Theta, 5 degree, we are going to get an image rejection ratio of what? 25 dB. High or low? This one is relatively low. You would like the image rejection filter to be, the image rejection ratio to be what? 50 dB and above. Are you following me on that? But because of this degradation, you are going to what? You are going to suffer a little bit. Clear? Clear? One of the homework problems I will be assigning tonight, not tonight, tomorrow. Tonight, all what I think about is food. I'm hungry. I'm going to ask you to derive this. Did you get my point or not? Straightforward derivation. Clear? But it's just a point to get the point across. Clear? Okay. So, any question? This, by the way, this is the ultimate goal. You put everything in a chip. We already talked about this. The challenge of integration. We already talked about this. By the way, the VCO, excuse me, the VCO, you need to make sure that it has a what? It is what? It is relatively what? Pure. A reformer does not have phase noise in it. And when we talk about the noise, I will show you the effect of the phase noise on the performance of the system. Let's get to the direct conversion. Clear? Okay. Let's skip this one and let's get to the diagram right away. And tell me what are the challenges. Tell me what are the challenges that we are going to face. First of all, let's quickly go over the receiver. This is the band select. Yes? Going to what? LNA. Yes or no? What is this is doing? What is this one is doing? Do we have an image? Do we have an image? No response. We don't have an image. Why? Because the local oscillator is going to be the same as what? As the desired channel. Yes? We are going to convert directly from the what? RF to the what? Baseband. I want you to see this and tell me, what do you notice here? UHF, whereas in the previous one was what? VHF. We are what? We are down converting. Excuse me. We are down converting immediately from the what? RF to the what? Baseband. Yes? Excuse me. Yes or no? Okay, so the LNA filter, this is again, it's a variable gain amplifiers. What am I doing here? I am what? Mixing I and Q. In which domain? Sorry, in which range? In RF or in baseband? RF, which means what? This one is going to be critical. The design of this one is going to be critical. Clear? And then what? This UHF, and again, I use the what? I use the low pass filter to get rid of the sum, and then what? Amplify it to just the audio amplifier along with what? The ADC and stuff like that. Clear? What is this for? One more time. What is this one is doing? This one. There is no image. This is not the image. This is not the image what? It is not the image rejection. I don't have an image. No. That's the channel select. Why is it so hard? That's the channel. Clear? Clear? Is this variable? This local oscillator. Is it variable or is it fixed? Huh? Of course it's variable. If the desired channel will change, you need to what? You need to change this one to be equal to it. Yes or no? Okay, good. This is variable. Are you following me or not? Okay, I don't have IF here. This is 0 IF. Let's see if you can help me with the problems. First of all, let's look at the diagram. This is the RF, and I'm going to what? Down converted directly to the what? To the baseband. Are you following me or not? This is the channel. This is our channel. Clear? Okay. Let's see some of the problems, and we'll continue next time. What? Say that again?
Oh, sorry. 5 minutes left.
But this one. I will show you this next time. I ran out of time. Okay. See some of the problems. Can we see some of the problems with the direct conversion? What do I have here? The channel is centered around what? RF. This is cosine. Is it possible that there is a leakage? If there is, look at how many types of leakage. You could have this leakage, or even worse, you could have what? This leakage, yes? And you are going to mix with what? With itself, generating a what? DC component that is within the what? The band of interest. Why? The band of interest is centered around what? 0. By the way, I'm assuming that the baseband is centered around 0. One of the possibilities to what? To eliminate this problem, the DC problem, which is we refer to, why do I call it DC offset? The value of the DC is going to what? Change depending on what? Depending on the signal. Yes or no? Okay. So, but to do that, one possibility to do that is to use a spectrum, the baseband spectrum, away from what? 0. Not centered around 0, but a little bit what? Away from 0. So that the DC offset will have no effect. You can use a what? A blocking capacitor to get rid of the DC. Yes? Can I use a blocking capacitor here? A blocking capacitor, it will take what? It will take the band with it. Remember, a blocking capacitor means what? A high pass filter. Yes or no? Okay, good. Now, is it possible that this one will what? Will come outside. That's what it means by what spur is. Remember what I told you about the spur? Spur is an unwanted signal. Clear? Okay. Now, how about this one? Tell me about this one. An interferer, an interferer leak. Yes? Notice, by the way, this interferer does not have to be at what? Does not have to be at the what? At the desired channel. Yes? But it leaked from the RF port to the what? Local oscillator port. And it will mix with what? With itself. Did you understand what I just said or not? Yes or no? This is also going to be here. Now, if I what? If I make the what? if the RF, if this, and see, this is the desired and this is the what? The IF. If this one leak in here, it will what? Mix with itself and generate what? This. What are these, by the way? What are these? These are the ones that are not leaking. Yes or no? If they are not leaking, this one will be mixed with who? This one, this component, will be mixed with who? With the RF, not with itself. Yes or no? Resulting in what? Resulting in these two components will not cause me problem. Do you agree? Because they are outside the what? The low pass filter. But the problem will come if it mixes with them what? With themselves. Yes or no? Okay, how about this one? I'll show you this next time. How about this one here? I have two interferers. Yes? And the nonlinearity happens to be what? Even order. Even, not odd order. Which means what am I getting? Second order intermodulation. What is the second order intermodulation? Please help me. Please help me. I have two what? Two interferers very close to each other, but they are what? Not within the desired band. Yes? If the nonlinearity is what? Even, which means what? For example, square law device. Am I going to get the second order intermodulation component, which is what? At what frequency? Second order. Omega 1 minus omega 2, omega 1 plus omega 2. You agree? Omega 1 plus omega 2, I don't care. Why? It's high. But omega 1 minus omega 2, if they happen to be what? Close to each other, it will what? It will be in the baseband. Yes or no? By the way, do I have that problem if the nonlinearity is third order? I don't have it here, but I have it in the what? In the heterodyne. Did you get my point or not? Yes or no?
Yes.
In the zero IF, I have the problem of what? The second order nonlinearity. The second order intermodulation component, which means I need to talk in terms of what? IIP 2, the second order intermodulation intercept point, rather than what? IIP 3, which we did in the case of what? In the case of the super heterodyne. Clear? Clear? In addition to all of this, we have what is known as what? The flicker. Have you heard about this? What does the spectrum of the flicker noise look like? Remember, for thermal noise, what does the spectral density look like? Constant. The flicker noise is what? Yes? It's inversely proportional to the frequency, which means what? At low frequency components, which is what I'm going to have, because it's directly to the baseband, I will have what? High power of what? Of the flicker noise. Are you following me or not? Somehow I need to get rid of this. Did you get it or not? Yes or no?
Yes.
Did I run out of time?
Just about, yeah. It's on 450.
It's not 450 yet? Okay, good.
Yeah, it's on 450.
Okay, cut me off. Why did we get bogged down today? We got bogged down. Why? Because of trigonometry stuff? I don't know. I was hoping to finish the entire thing. Did you get it? But anyway, did you get the... yes or no?
And this concludes EE 544 on Thursday, January 30th, 2014.